Hey, good morning, everybody. Welcome to VSPG. This week we have a second presentation from Dr. Elizabeth Turner. Elizabeth was able to step in in a time of need when somebody had to drop off the schedule due to other complications. So we're really thankful for that. This week's presentation. Oh, Elizabeth, if you'd like to share your screen, that'd be great. This week's presentation is titled Exploring the Timing, that's a little different, or Controlling Factors at the Intersection of Sedimentology and Mineralization in the Neoproterozoic-hosted Basin, Central African Copperbelt, Democratic Republic of Congo. Next week, we'll hear from a PhD student at Penn State, Benjamin Barnes. We're trying to get more PhD students and postdocs, early career scientists present. So we'd like to have good support for them from the audiences here. So join next week for his presentation. With that, I'll give a couple of announcements. We do have our schedule filled up until the end of the year, but it's not posted yet. I will post that most likely before next week. But we're going to do something different at the end of the year. Some of the issues that we've had are just the fact that this is a worldwide seminar series, and it's been hard to get people in certain time zones to be able to present. So what we're going to do at the end of the year is we're going to shift our time to 5 p.m. Pacific. And we have 6 speakers lined up from both China and Australia. We'll call this, I think we're going to call this VSPG After Dark. So we're going to do that for 6 rounds in November and December and see how it goes. And we'll probably do another one next year as well. So with that, I don't think I have much more to say. Andre, please introduce Elizabeth for us.
Yeah, great. Thanks, Alex. So just a couple words on schedule. So we will continue at 8 o'clock until November, and November, December, Alex organized sort of the 6 sessions. And we will take a break from early June until early September. So with this, it's a pleasure to introduce Elizabeth Turner. She was trained as a sedimentology stratigrapher at Queen's University, mostly worked on carbonates. And after she finished PhD at Queen's University, she worked for some time in Geological Survey of Canada office in Nunavut, and I guess that's where she picked up interest in economic geology. And today she will be talking about one of the largest copper mineralization system in the world, hosted in Neoproterozoic-hosted basin, that record Cryogenian glaciations and other changes. So with this, I pass to Lisa. Oh, and I forgot to mention, she got Robinson Award from GACMAC, and this talk is one of 2 talks she gives as a tour of Canada. So with this, I pass it to Lisa.
Thanks, Andre. I trust my slide is showing all right. Okay, thank you everybody for coming to my talk. Like my previous talk back in March, this one is part of a different lecture series that's designed for a general geological audience, including undergrads, but hopefully you'll find something worthwhile in it nonetheless. I offered this to Alex and Andre just to fill a gap in the schedule because it fits well with the Precambrian theme under the subheading of ore deposit geology. So the Central African Copperbelt is a really important ore district, which is bedeviled by some controversy over both the timing and the nature of the ore forming events. And so this talk is absolutely not specifically about ore characteristics or an investigation of ore forming fluids or events. Instead, it's a work in progress, unpublished, that uses old school methods to address problems of timing in ore ore formation. And so for this, we're using sedimentary, diagenetic, hydrothermal, and structural characteristics of a very characteristically Precambrian rock type, Cryogenian diamictite. And in this case, it hosts the enormous, very unusual, recently discovered high-grade Kamoa-Kakula copper deposits in Congo. So we don't think nearly enough about Africa. Africa is underlain by several cratons shown in pink. So the West Africa craton up here to the northwest, Congo craton in the middle, Kalahari craton in the south. And these are separated from one another by mobile belts, which were in part rift basins that developed during disaggregation of Rodinia, and they were then affected by deformation during the Pan-African orogeny. That's the late Neoproterozoic to early Paleozoic event in which Gondwana amalgamated. And the Central African Copperbelt is here between the Congo and Kalahari cratons. The Pan-African event, so between 600 and 500 million years ago, was the last real tectonism in the area. There was mid to late Paleozoic glaciation in Africa, and that was pretty much the most recent glaciation. So since then, we're dealing mainly with chemical weathering in a mainly tropical environment. So Central Africa is an area of deeply weathered bedrock and almost no natural exposure. So it's quite challenging to work there. There's effectively no outcrop. Everything has to be done using core, and core exists only in the immediate vicinity of ore deposits. So the geographic distribution of information is quite sparse and uneven. So Central African Copperbelt is a sedimentary-rock-hosted district in Neoproterozoic rift-related strata of the Katangan Basin that was affected by the Pan-African event, which is locally known as the Luphilian orogeny. The sedimentary-rock-hosted copper system is summarized in the timeless paper of Hitzman et al. 2005. And just so we're on the same page, I'm going to walk us through the requisites of the system. The metal source is inferred to be continental red beds in which the sediment grains have diagenetic coatings of iron oxyhydroxides that also contain loosely held metals like copper and cobalt. And this source rock is then exposed to a metal scavenging brine, probably derived from evaporate dissolution, which can also be the sulfur source. The fluid then convects or migrates, causing further red bed alteration and leaching the loosely held metals. And the now slightly metalliferous fluids, and I'm talking slightly, so like 100 parts per million or so, migrate through conduits and become trapped in propitious locations like under aquicludes or in antiforms, where a pre-existing reductant is already in place, so hydrocarbons or pyrite or something like that. And there may be an event that causes the fluid to move, so tectonic stress, maybe gravity-driven flow from an orogen or salt diapurism, a number of possible triggers. In the Central African Copperbelt, we're dealing with an intracontinental rift basin, and this diagram summarizes, another Hitzman diagram, summarizes the possible times in the evolution of a rift basin when copper mineralization can take place. So early in the basin's depositional history, brines that are produced by compaction can cause red bed alteration and mineralization. Farther along in the basin's depositional history, the rift becomes flooded with marine water, as they do, and becomes occupied by marine strata, shown by these layers at the top, which includes evaporates in pink. And the evaporates can be dissolved in the subsurface to produce the necessary brine, which then does its thing in the red beds and is then focused through faults and into structural stratigraphic traps where the reductants are already present. Mineralization can also take place long after the basin's depositional history has ended. So hydrothermal fluids associated with orogenic events or basin inversion or salt diapurism, these things can take place, long after the rift is done. So you can see there's a wide range of times when copper mineralization can take place, and there's potential for multiple events to affect a given district. And of course, timing and ore system models are important for exploration vectoring. So, especially in this district. So deciphering what truly happened and when is critical. Lots of opportunity for controversy over what exactly happened in a given deposit or district and when. And this highlights a major controversy bedeviling the understanding of the copper belt in general. There are a number of plausible stages in basin evolution during which mineralization is possible. But the ability to figure out the timing of the mineralizing episodes is problematic. And I'm not talking just about, dating issues. Most of the dating so far indicates Luphilian or later mineralization. So Luphilian between 600 and 500 million years approximately. And you can see there's a lot of dates in that range, which might give a person a strong bias about the age of the district as a whole. But a big and hitherto neglected problem is that commonly the paragenesis of the dated material is not adequately characterized. In other words, it's difficult to link the date that's been produced to textural evidence that conclusively indicates which stage in the basin's history is captured by the date. So, sometimes what you see is, the dated mineral is spatially associated with copper cobalt sulfides. And, given the backdrop that I just described, that may not be adequate to characterize the paragenesis of the dated material, given that it's possible that a deposit may have experienced multiple stages. So in other words, the possibility of ore reworking during successive fluid events could at least hypothetically mask earlier events, or even lead to misleadingly young dates. So what I'm emphasizing today is that boring, time-consuming, fussy, old-fashioned petrographic approaches should be an essential part of all of this if we want to properly understand a deposit's origin and its timing. And it may be quite difficult or impossible to untangle given the degree of alteration in this very complicated district. So an example of this is a recent flurry of heated papers, started with some new Riaz molybdenite dates that seem to indicate strongly that most mineralization is Luphilian or younger. But so regardless of what stratigraphic level they're in. But the discussion papers that ensued point out that that molybdenite is in the copper belt exclusively associated with syntectonic mineral assemblages, that is to say, Luphilian. So in other words, although these new dates are probably accurate, they may well unintentionally be paragenetically selective for late mineralization or late remobilisation. So maybe they don't capture the whole story. The Katanga Basin is, for the most part, a rift basin. It has several episodes of extension down here, and a final stage recording a foreland basin associated with the Pan-African orogeny. And there's no scale bar on this strat diagram for the Katanga supergroup because thickness of these units varies dramatically from place to place, which is typical of rifts, but we're talking numerous kilometers of thickness. And the column is color-coded with blue for carbonates, yellow for sands, and there's an important sand right here in the middle. Green is for other siliciclastics, and purple is for evaporates, which are critically important in the district. The maximum possible depositional age is in the upper 800s based on young granites that cross-cut Paleo and Mesoproterozoic basement shown in dark green and blue. So the overall age is clearly Neoproterozoic, that is to say Tonian, Cryogenian, and Ediacaran in the current terminology. So the Katanga supergroup consists of three groups: the Rowan group, the Nguba group, and the Kundalungu group. We'll talk quite a bit about the Rowan group. They're divided by the position of two diamictites, the Mwale formation, or informally known as the Grand Conglomérat, which is at the base of the Nguba group, and the Petit Conglomérat at the base of the Kundalungu group. And these two diamictates are affiliated with the Sturtian and Marino and glacial episodes of the Cryogenian. So this means that we're dealing with a huge rift system that was twice influenced by glaciation of some sort. The Rowan group consists of rift-related siliciclastic rocks, sands, and conglomerates at the base, overlain by a thick evaporitic interval in purple and eventually some odd carbonates in blue. And the traditional Zambian copper belt is hosted by reduced mud rock near the base of the Rowan group. The traditional Congolese copper belt is hosted by the same strata, but in Congo, the lower Rowan group is largely disarticulated into giant clasts, hundreds of meters to kilometers in size, that were rafted up in evaporate diapirs along tectonic welts during the Luphilian event. So that's what the asterisk indicates. The top of the Rowan group indicates, has evidence of rapid deepening, and there's large amounts of siliciclastic detritus sands entering the basin around its margins. That's called the Mwasha subgroup. And this heralded the deposition of the Mwale Formation, the Grand Conglomerat, which is the host of the Kamoa-Kakula deposits that I'm going to be talking about. So the Mwale Formation diamictite is over 1 kilometer thick in the Kamoa area near the edge of the basin. Above the Mwale is a succession of carbonates and fine-grained siliciclastics, then the Petit Conglomerat linked to the Marinoan glacial episode, followed by another succession of fine-grained siliciclastics ranging up into the lower Paleozoic. And this upper part accumulated in the foreland basin of the Luphilian Arc, which is the local name for the Pan-African event. So here's a map of the Central African copper belt. The dashed line shows the Zambia-Congo border. So Congo kind of pokes down into Zambia. And the Katanga Basin, which is this area in the middle, overlies and is flanked by Paleoproterozoic and Mesoproterozoic deformed metasedimentary rocks shown in blue and green. And these are punctuated by Mesoproterozoic granitoids. The Luphilian Arc consists of several tectonic subdivisions with increasing degrees of deformation and metamorphism going southwest into Zambia. In the north is the foreland basin, which is poorly exposed and poorly known, has little economic prospectivity. The Congolese copper belt, and I'm going to now point in the upper diagram, is mainly in the fold thrust part of the arc, but the westernmost part of it, and I'm pointing at the bottom again, where Kamoa-Kakula are, and misleadingly called the Western Foreland, consists of very gently folded, minimally deformed strata. In Zambia, the traditional Zambian copper belt is down here in the southeast. It consists of stratiform mineralization in strata that flank this big basement antiform. But elsewhere, as you go west, these so-called basement domes are associated with more complex ore types in a more highly deformed and metamorphosed region. This little diagram in the upper left, again, a Hitzman diagram, summarizes the really wide range of copper deposits types and their distribution. In the traditional Zambian copper belt, in the southeastern part of the arc, the ore shale is low in the stratigraphy. So here on the lower right, the yellow unit is the Rowan group, and it's the lower Rowan group, and the ore shale is shown. I mean, you can see all the showings in past producing deposits. So it encircles these basement antiforms, and then you can see the fold thrust belt, extending away from it. Farther west in the domes region, the rocks are more deformed and metamorphosed, and mineralization occupies, this is a map from the Kansanshi deposit, mineralization occupies veins and surrounding altered strata over the antiformal domes, like such as here. So totally different kind of situation. In Congo, it's a different matter altogether. The main part of the Congolese copper belt is in the fold thrust district, where the ore is hosted by the same stratigraphic unit as in the Zambian copper belt. So I'm pointing in the upper left here. So these red things are the ore hosting unit, which is now disarticulated into giant slabs that have been rafted up in these evaporate diapirs in welts in the fold belt. And so this map on the lower right from Tenke Fungarume is, it shows these, so that the contiguous strata of the thrust sheets, and then in blue is the diapiric Rowan group that's been rafted up, and clasts of it shown in darker blue with the ore shale or the ore unit in black. So that's sort of typical of the main part of the Congolese copper belt. But over in the Western Foreland, where Kamoa-Kakula are, the ore hosting unit is much higher in the stratigraphy. And in fact, the basal Rowan group is absent because the Nguba group lies very close to the basement. This is a depositional effect owing to proximity to the basin margin. And these strata, so you can see here's a picture, a simplified map. You can see that there's antiformal structures over which the strata are very gently draped in the Kamoa-Kakula area. And here from the Ivanhoe Mines website is a map to give you a general idea of the exceptional grade and aerial extent of these deposits, which cover many tens of square kilometers in the subsurface. And the deposits are jointly owned by Ivanhoe Mines, which is a Canadian company, the Chinese company Zijin Mining Group, and the Congolese government. And the Kakula mine went into production last May. So if you've ever seen Kamoa-Kakula ore, say at Korshak, at PDAC, you'll know that the ore is hosted by diamictite. And gentle reminder for those who are not sedimentologists, diamictite is a word that has no genetic implication. It's merely descriptive. It refers to completely unorganized particles of all sizes. So by unorganized, we mean no grading and no preferred orientation of particle long axes, regardless of their size. So clay or boulder, doesn't matter, completely random orientation. So this is a rock that contains no depositional texture. And in this case, the diamictite was deposited as many amalgamated debrites. Okay, so debrites are the deposits of debris flows. That's a process. And the larger class, and by larger, I mean, bigger than about 1 millimeter, they're suspended in a matrix of finer grained material. So the larger class consists of lithic fragments derived from the nearby basement, so mainly metasedimentary rocks. But the diamictite matrix, where it's not mineralized, consists of quartz, case bar, albite, chlorite, dolomite, and framboidal pyrite. And there's not a whole lot of geographic variability in this combination of materials, although the relative proportions do change. And the ore is especially eye-catching, unfortunately, because of the presence of these amusing sulfide and gangue caps and sometimes beards on the larger class, on some of the larger class. And this is really very distracting, because in reality, most of the copper grade is conferred by disseminated sulfides in the matrix. Okay, so we have to really discipline ourselves to stop being distracted by the eye candy. So the Kamoa-Kakula deposits, as I said, are near the western periphery of the Katangan Basin. These are stratiform deposits that are hosted at the base of a thick succession of diamictite. Okay, so here's a scale bar, 200 meters. Moale Formation is well over 1 kilometer thick in this area. And this is material that was deposited during rifting of Rodinia. The material is mainly derived from nearby newly faulted basin margins, probably with some component of a glacial influence. And here are the indicated resources for those who care about that sort of thing. I'm just interested in the puzzle myself. So in the Kamoa subbasin, most of the lower stratigraphy of the Rowan group is absent. Okay, that's the part that's mineralized in the Zambian copper belt. And over here, it's depositionally absent, owing to onlapping onto these basement highs that are shown up here in green. Okay, so it's important to note this because it's probably the reason why the mineralization is higher in the overall stratigraphy. The lower Rowan groups, which act as a reducing trap elsewhere, are not present, and instead the lowest reduced unit is the pyritiferous basal Moale Formation diamictite. Among the previous work on Kamoa-Kakula is a paper by Schmant et al., who laid out a lot of the basic information. This paper was quite wide-ranging. trying to establish all of the basic stuff all at once. And among the many things that they addressed in this paper, they used ChemScan, which was a new technique back then, to decipher the distribution of and relationships among the matrix minerals. And they established a paragenesis for Kamoa that involved a single ore forming event that predated the Luphilian orogeny. Another important thing to come out of this study is that the ore zone, so this lower part of the Mwale Formation, is vertically zoned, okay, with respect to copper minerals, with minerals of decreasing copper content going upward. So chalcocite at the base, then bornite going upward, chalcopyrite, and then pyrite once you get above the ore zone. And although this paper didn't draw attention to another fact, sometimes the copper mineral in the matrix is not the same as the copper mineral in the caps on the larger class in the same sample, okay, which is perplexing and probably incredibly important. Another student thesis focused on the origin of the sulfide caps and beards. This was done by Frank Tweekde. And he identified these things as strain fringes that developed during the Luphilian deformation. And because the strain fringes do contain concentrations of copper minerals, this paper concluded that mineralization was a Luphilian event. And of course, this is not compatible with the totally different study of Schmidt et al. So when my group got the opportunity to work on these deposits, I decided that a really important and probably difficult thing to address would be the paragenesis of the diamictite matrix, given that that's where the ore grade is. And so I had a very wonderful master's student who started this study, and then I've been following up with more detailed work as I'm able to under the current circumstances. And so we focused mainly on high grade and unmineralized diamictite from the Kakula deposit. So here's a plot through a high-grade hole at Kakula. The ore zone here is several tens of meters thick. Also plotted is the identity of the disseminated opaque minerals. So chalcopyrite, bornite, chalcocite, bornite, chalcocite, chalcopyrite going upwards, and then pyrite once you get above the ore zone. So strong vertical zoning and copper content of the sulfide phases. There's also hematite in the ore zone, which is paragenetically slightly later relative to the ore sulfide. And just so we can get it out of the way, and because in fact it is important later, the irresistible caps and beards consist of a combination of sulfide and gangue minerals. Okay, so we're going to zoom in on the box, and so you can say you've seen this stuff. So here are images in reflected light, oblique incident light, and cross-polarized light of the same area, that top of that clast. You can see that the clast consists of a quartzite clast, and the cap consists of chalcocite, which is sort of whitish in reflected light, quartz, which is these areas here, and chlorite, which are these fibrous looking zones. And so you can see that the edge of the quartzite clast is where the dashed line is, so little equant particles inside, elongate quartz domains above, where they interact with the chalcocite and the chlorite domains. So my point here is that the caps are not replacive, which is quite perplexing. I mean, in some cases, there is an element of replacement. For the most part, they are accretionary, however. And the detailed paragenesis of the caps is absolutely a separate story from what I'm talking about today. So we're now going to mentally block out these distracting caps and address the matrix, which has some extremely subtle but important characteristics. Okay, much of the matrix is completely textureless. Okay, but locally the long axes of the matrix minerals are aligned in quotation marks. And it's tempting to call this foliation right off the bat, and eventually I will. But initially we wanted to use, or we wanted to avoid using an interpretive name for this phenomenon, given that Schmidt et al. Interpreted the entire paragenesis as hydrothermally derived with no tectonic influence. I mentioned that the bulk of the ore at Kamoa-Kakula consists of disseminated fine-grained copper minerals in the matrix, and these reflected light images show typical high-grade ore from Kamoa. you will see in the lower right that some of the sulfide particles, these ones are bornite, are spherical and clearly replaced pyrite framevoids, whereas others are clearly not like that at all. So what I'm going to do is take you through a brief tour of some matrix characteristics that ultimately bear on the timing of mineralization and ultimately on the origin of the not so terribly important but terribly distracting strain for, caps and beards. Okay, so I'm using a combination of image types. They're all labeled. Some are translimited light, reflected light, backscatter electron images, and all of them are stratigraphically oriented with up to the top, unless otherwise marked. So first, we're going to start with the non-aligned matrix in the least altered material to get a baseline. So here's what that looks like at some distance above the high-grade zone at Kakula and geographically away from it. So the matrix is dominated by quartz, K-feldspar, albite, chlorite, dolomite, and framboidal pyrite. The source of the detrital components is local basement exposures. A framboidal pyrite is syngenetic, so syn sedimentary, meaning that it formed more or less right at the seafloor, which is what framboidal pyrite does. Much of the matrix is comparatively textureless, but locally it's subtly foliated or aligned, as we say. So we're going to look first at the non-aligned matrix, and I will show you how incredibly textureless it is. And we're going to zoom in on this area around this volcanic clast. So here we are. There's an area down here with no alignment, and then around this volcanic clast, you can see there are areas where there's vague alignment of the matrix minerals. So we're going to zoom in on this white box first, and still in plane polarized light, you can see there's no preferred orientation or distribution to the sand-sized and larger silt-sized particles, which are transparent in plane polarized light. So they're roughly equivalent, but they have a slightly longer axis, and these longer axes are randomly oriented. There's also no horizontal fabric here of the type you'd get from compaction, kind of compaction that's normal in fine-grained siliciclastic rocks when they get buried. So this material is quite totally fabricless. If we zoom in yet again, whoops, wrong one. It's getting hard to see clearly because the size of the very small matrix particles is much larger than the 30 micron thickness of a thin section. But nonetheless, I'm going to torture you with yet another image. So here at the highest optical magnification, 10 micron scale bar up on the right, there are small clear quartz grains. There's some pyrite, different types, different story, and a plethora of individual flakes of chlorite, these spiky things, all at random orientation. So there's no texture in this matrix at any scale, depositional or otherwise. And so we can't really figure out at this point what's going on with the matrix because the grains are too small to work with optically. We have to turn to backscatter electron images. All right. So here we can start to get an idea of what actually happened. Once again, there's a complete absence of fabric up here in the upper left. There are detrital grains of quartz and feldspar. These are the darker gray things, less of a backscatter signal, and chlorite, which is the paler gray. And you can see, these are detrital grains. They have detrital, or at least detrital-derived shapes, and they're 20 microns in size or bigger. But that's not what I'm interested in. I'm interested in the really, really small matrix stuff, which is where the bright specks are, that's where the sulfides are. And so zooming in on an area of the really finest grained material, you can see it consists of, this is not a sedimentary fabric at all. These are not sedimentary particles anymore. This is a scaffold of randomly oriented chlorite flakes in paler gray that kind of make a framework in which the darker material, which is the quartz and the feldspar, actually fills the spaces among the chlorite plates. And the black things are actually pores. These are empty spaces that are in large part, so they're quite irregular, and a lot of them have planar surfaces. They are in large part defined by planar crystal faces of this meshwork. So in other words, the tiny voids are voids in an interlocking mesh of super, super fine-grained matrix particles that formed by recrystallization. The finest grained part of the matrix is entirely recrystallized, right? No longer containing any sedimentary fabric. Okay, so that's one end member. Let's move on to the ore zone matrix. At the other end of the spectrum, sort of the most altered matrix. And so the matrix in the ore zone has a different mineralogy. Some of the previous minerals are still present, quartz, case bar, chlorite, and dolomite. But the new minerals present are the copper minerals, a profusion of muscovite, and some hematite and rutile. And none of these minerals exhibits any preferred orientation or other form of texture. The quartz, the case bar, and the dolomite particles are equidimensional, important, and they're intergrown with one another. Okay, the copper mineral in this particular example is chalcocite, and you can see some of the smaller ones are, roughly the size of maybe framboids, but they certainly don't have the same shape. Some of the other chalcocite grains clearly are pore filling, and the hematite also occupies pores in the matrix. So all of the grains, except for the phyllosilicates, which are the paler gray things, are equidimensional, and there's no fabric, no foliation, no alignment. And there's a lot of porosity, right? And at least some part of that porosity is actually defined by crystal faces of some of the minerals, so these sharp looking surfaces. But some of it is a bit more ragged and probably has a different origin. Here are some really magnified pictures of the hematite and chalcocite, just to convince you that at least some of the sulfide and oxide phases fill pores. They envelop the protruding planar subhedral to euhedral surfaces of the matrix minerals that form the margins of the pores. Okay, let's go back to the least altered matrix and look at the tiny patches of aligned matrix look like. Okay, so the main difference between non-aligned upper left and aligned lower left least altered matrix is that many of the larger silt and extremely fine-grained quartz particles have rotated their long axes into the plane of an alignment that's defined by chloride. Okay, so the silt quartz grains still have the same sizes and shapes in the aligned matrix as in the non-aligned matrix, but for most of them, their long axis is now aligned with chloride. On the lower right is a thin section that is cut horizontally as opposed to vertically in all of the other examples. And you can see there is aligned matrix, these little areas that they're vertical, so it's going in and out of the screen. They're discontinuous. They wrap around the large clasts, depicting several subparallel areas of foliation, not very big. And they're also parallel to what seems to be a spaced cleavage off in a matrix. In carbonate world, we would call these pressure solution seams or stylolytes, and I have no trouble with that. Let's go back to the least altered matrix and look at what the aligned matrix in the ore zone. And so this is from Kakula ore zone. This is in the high grade zone. So remember that the mineralogy of this is different. There's an abundance of copper minerals, hematite, and muscovite. And we're going to zoom in on two areas. One of them over here on the left is an area between two quote unquote large clasts. And yes, this little tiny thing over here qualifies as large. And then over here on the upper right is an area underneath a large class where there's non-aligned matrix to the left and aligned matrix to the right. So we're going to start on the lower left one. Okay. And so here, the matrix is aligned in a tight spot between two large clasts. If we zoom in on the right, higher magnification, you can see that the phyllosilicates, which are in the paler gray, are all vertically aligned. The long axes of most of the larger particles, so that's these ratty looking things, are also very strictly vertically aligned, very, very elongate. And the copper minerals in the hematite, so all the bright specks, are no longer equidimensional. They too are aligned with the phyllosilicate foliation. Oh, and I'm calling it foliation now. Okay, the quartz, which is these solid dark gray things, are extremely elongate and no longer equidimensional at all. They have long straight surfaces parallel to the foliation, and their tips have ragged protrusions, some of which I've highlighted with arrows. And just for the record, this is not the sort of thing that ChemScan is going to give you. You have to do the drudgery yourself. So here's where things get more interesting, or even more interesting. Okay, so given the sharp differences in composition and fabric between aligned and non-aligned orozone matrix, we decided to see what it had to do with copper content. So my student went off and looked at this right area from the previous image. At the top, we have a class at the top, some non-aligned matrix below it to the left, and aligned matrix below it to the right. On the lower left is an X-ray element map that shows the aligned matrix. So the lower right has more muscovite in blue and less quartz, so the black dots, and less dolomite, green dots, than the non-aligned matrix right next door, just a couple hundred microns away. So this is not, a depositional compositional thing. Here's another map of the same field of view in which the copper minerals are coded in blue and the hematite is in red. And so you can see that copper seems to be more abundant in the non-aligned matrix than it is in the aligned matrix. And conversely, the hematite is more abundant in the aligned matrix than in the non-aligned matrix. So clearly something's going on. So my student then went off and systematically went through the stratigraphy of the orozone in several holes. And in each sample, he analyzed a small number of areas, so that's the N, of aligned in blue, non-aligned in blue and aligned matrix for their copper content using SEM-EDS. So just a really crude way of getting something approximating a mini bulk composition. So here's a high-grade hole at Kakula, and stratigraphy on the left with the different copper minerals going up, grade in the red histogram. So clearly there is a strong differentiation in copper content on the horizontal axis between the non-aligned matrix and the aligned matrix, even using just this crude method. So matrix in the orozone consists of minerals that are equidimensional in non-aligned matrix, but elongated in aligned matrix. And we're not including phyllosilicates because they don't have any choice. So what does it all mean? Most of the matrix minerals are much, much too small to contain accessible information. But some of the larger quartz, silt, and very small quartz sand grains are thick enough to be transparent in thin section, right? The thin section is 30 microns thick. So let's look at them. We're going to zoom in on this utterly random grain right here in a zone of aligned matrix next to a large clast in the upper left. Okay, so here's my best friend in a backscattered image on the lower left, shows nicely the alignment of the surrounding silicate, sulfide, and oxide minerals. The quartz grain is elongate. The sides parallel to it are very sharp and smoothly curved. However, towards the ends, where it trails off to the matrix, there are inclusions of phyllosilicate minerals. So these are the laths down here, at the bottom and at the top. So the quartz clearly, the grain clearly encloses phyllosilicate flakes near the upper and lower tips of the quartz. And you can see that in this reflected light image as well, or at least on the lower part. I seem to have chopped off the upper part. Next image is a partly cross-polarized image of the same area, and it shows that the quartz particle is a single crystal optically, even where it encloses the phyllosilicate flakes. Okay, so there they are. And so it's the next image that's really going to tell the whole story, actually. This is a cathode luminescence image, and in which you can see that although the grain is optically continuous throughout, so a single crystal crystallographically, it has sharp compositional breaks down at the bottom and at the top. So cathode luminescence signatures are conferred by the trace element content of the quartz, right? And so clearly there's a different trace element content at the tips, which are optically continuous. So these are microscopic syntaxial quartz overgrowths on an original detrital particle whose margins are marked by these sharp CL signature changes. And where the syntaxial overgrowths are, there are enclosed phyllosilicates from the matrix. Okay, so this is really cool. Very tiny. This type of microfeature is actually ubiquitous in the orozone aligned matrix once you know how to look for and see it. So we're proposing that these are mini strain fringes, just like those that Frank Twitta interpreted for the comparatively huge and much more exciting to look at, sulfide gangue caps. How does it work? Well, the sharp curved particle margins are where quartz was removed by pressure solution during the Luphilian compression. So horizontal compression, highest zones of pressure would be facing into the horizontal sigma 1. And so the small amounts of solutes produced here and migrated to the nearest low pressure zone or lower pressure zone where they precipitated to produce these syntaxial overgrowths. And pressure solution is an extremely familiar phenomenon in sedimentary geology. This didn't surprise me at all. If you subject a sedimentary rock to pressure, you will get pressure solution. Right? So although it's probably too small to detect in the finest matrix grains, and only some minerals give good cathodoluminescence signatures, most of the tectosilicate, the framework silicate minerals in the matrix may have been pressure solved to at least some extent in the tiny, tiny patches of aligned matrix in the ore zone. The phyllosilicates seem to have been resistant to pressure solution. They became concentrated in the aligned matrix, as I showed in that X-ray map. They seem also to have enhanced the dissolution of other minerals that were in contact with them. And this is, also a really, really familiar phenomenon in carbonate diagenesis. As for the copper minerals, they seem to have been the most readily remobilized by pressure solution, and their preferential removal in aligned matrix produced the difference in copper content between aligned and non-aligned matrix in the ore zone. And that, of course, unavoidably suggests that the disseminated mineralization was early and then was followed by tectonic pressure solution and remobilization, and that some of the solutes that were liberated by pressure solution were then able to migrate into the very large low pressure zones at the tops and bottoms of the larger class, where they reprecipitated as the strain fringes, the caps and beards. So this seems rather fussy and tiny, but actually this is like, kind of an unusual place where we can actually get hard textural information that shows, using these really old school approaches and the principles of relative dating that we teach our geology students in first year, the how and when of two very distinct episodes in the mineralization history at Kamoa-Kakula, one prior to the Pan-African orogeny and one during it. So the paragenesis of Kamoa-Kakula starts with sedimentation of diamictite as debrites and the formation of syngenitic pyrite framboids, all forming a textureless matrix depositionally. And then in the ore zone, during a comparatively early event, early in quotation marks, the pyrite framboids were replaced by copper sulfides and then probably zone refined to produce that upward decrease in copper content and the remobilization of copper minerals out of the framboids and into pores. And at the same time, the matrix minerals recrystallized, the really finest grain stuff, and muscovite appeared, shown in the white dashes. So the resulting crystal mesh is completely textureless. Lots of porosity remains, defined by the crystal faces of the meshwork. And the lack of fabric indicates that this recrystallization took place under no deviatoric stress, so at some stage prior to the peak Luphilian. And then late copper remobilization took place through pressure solution and syntaxial reprecipitation on individual tiny, tiny tectosilicate, carbonate, sulfide crystals, forming micro strain fringes on individual grains in aligned matrix, and also from beside the larger class into the strain shadows, the caps and beards on their tops and bottoms. And the horizontal stress responsible for this could only have been part of the Luphilian deformation event between 600 and 500 million years ago. So none of this, as I said, is particularly intended to address the nature of the earlier or late mineralizing fluids, but there are some hints, and it's a different thrust of the work that we're doing. I'm very pleased that we can offer some firm textural evidence for a two-stage ore paragenesis at Kamoa-Kakula, two phases that may well have been temporally distinct, widely spaced by as much as 100 million years or more, possibly. But word of caution, this is a work in progress. It's really been in suspended animation for over a year, thanks to circumstances beyond my control. I'm hoping to now complete this part of my works group and bring it to a publishable state and possibly eventually produce some dates for these textural events that I've identified. So thank you all for coming to my talk. Hope it wasn't too ore deposity for this group.
Thanks, Elizabeth. I thought it was really great. I enjoyed seeing all of your pictures and your VSCs and your microscope stuff. So we'll transition to our Q&A. So either people can raise their hand or type into the chat, or and I can ask if you type into the chat. So we'll give people a second to get their thoughts together.
So maybe I start, Liz.
Okay.
So I guess you suggest that was an early event that was not related to the fabric, and yet probably it was some event that drove brines and fluids to transport metals. So I'm wondering, what is this event? Is it some tectonic event that wasn't recognized, and deformation happened on a shallow structural level and it didn't produce foliation? Or what is the driver for this large scale fluid circulation that apparently affected sort of huge area and resulted in this giant deposit?
This is the endless problem of the copperbelt and other red bed districts is, what actually drives fluids when there is no evidence of tectonism. And so, you have to go back to the people who established the red bed model for possible explanations, and those were the explanations that I provided with the cartoon early on. There are ways in which fluids can be circulated without having a tectonic influence. And they have to do just with the endogenous processes in the basin, the density contrast between a brine that was produced by evaporate dissolution, displacing pore fluids of lesser density as they descend, generally through structural conduits, and picking up metals as they do so. So there is certainly in the ore deposit modeling literature a viable way of producing metalliferous fluids that are saline and oxidized and can move around without a tectonic influence. Interesting to me is in the red bed literature, there really isn't a whole lot of work that's been done on the diagenesis of the putative source rock, right? So like what happened in those red beds? They're commonly very, very altered, and it's really tough to work on. But I think this is one thing that really needs to be done. And there may be potential for at least relative dating, if not absolute dating, of some of the diagenetic products that can be linked to the ore system. And we've done that for a copper system in the Arctic islands of Canada, and that's moving towards publication at the moment.
And in a stratigraphical record, you don't see any unconformity or time breaks or sort of erosion of unit that you can relate with some maybe movement in the basement or tilting or anything, maybe not a major tectonic event, but sort of distal impact of some tectonic events.
Yeah, there are some possible unconformities. So using carbon isotope and kind of work your way through the Rowan group and also through the Nguba and the Kundalungu if you have the right place. It's really hard to get this kind of information, and it's very spotty, and it's not nice like it is in Namibia or Oman. But yeah, there are ways of identifying possible unconformities, but then none of them really have a whole lot of evidence for anything other than some kind of a eustatic signal. So there's been sequence stratigraphic work done, at least for the lower part of the Katanga supergroup, all of which kind of forces it into a framework that is depositional. So I can't really answer your question. And it comes back to the whole problem that the information in this district is so spotty, and everything is so severely altered, and the spacing in between things is so far and so patchy. Identifying a real unconformity, I mean, there's no outcrop, right? So you're just working with core in tiny little patches. So it's possible that I could answer yes to your question if I had more information, but with what I have and what I've done so far, which is admittedly, not comprehensive. So far, I can't give you a yes on that.
Okay, looks like we have Stefan, and then we'll have Greg, and then a couple in the chat. So Stefan, please unmute yourself.
Bonjour, Elizabeth. Thanks a lot for your presentation. I'm not that familiar with the Zambian copperbelt, so it was a good overview for me. I was just wondering, could you compare the early mineralization with some style of mineralization we see, for example, in MVT deposits or sandstone or lead-rich sandstones, where some of these are thought to have been formed in foreland settings contemporaneous with orogenic contraction? And if some of those late mineralization in the pressure fringes could be related, let's say, to a later peak, but in the same orogenic cycle. So this would put in question the early timing in this complex setting of mineralization.
Sure, yeah, and please note that I used air quotation marks for early, so yeah. Comparatively early, just meaning pre-peak Luphilian, with who knows? I mean, the range of possibilities of non-tectonically influenced fluid mobilization events is open for that stage. As for how it compares paragenetically and texturally, carbonate-hosted zinc deposits, there is really no comparison, actually. So the mineralization, the early mineralization in this particular area, well, obviously not carbonate hosted, it does consist of these replaced pyrite framboids, and this is like undisputed that the pyrite was providing the reductant for the incoming copper, and there are also I think there's a certain amount of zone refining. In contrast, as you mentioned, carbonate-hosted districts where fluids are introduced into much older rocks by, like say the topographically driven fluid model, there's a lot of variety in the textures that result, but it's not necessarily replacive, and very commonly there are textures indicating brecciation and void filling. So I don't see too much by way of textural comparison between this and comparatively early type mineralization in carbonate-hosted districts, so-called MVT districts. Does that answer your question?
Yeah, okay, thanks.
Thanks.
Yeah, can I jump in here? That was a lovely piece of detective work. I enjoyed that.
Thank you.
I'm with you on the sedimentation, Cryogenian 700 and the remobilisation 600, but it seems to me the remobilisation depleted the ore rather than improving it. And I wonder if you even need the intervening mineralization phase. Could it be that what you're looking at is a placer deposit from a glacier of a pre-existing deposit? In other words, the mineralization predated deposition and is just being moved like a bulldozer moving stuff around in a quarry.
Yeah, so the basement rocks don't contain a whole lot of framboidal pyrite or pyrite at all. They're mainly metasiltstones and sandstones, and they're pretty bland. Framboidal pyrite is a syngenetic and epigenetic thing. It forms in the water column at the bottom of a euxinic water column and in the very, very shallow sediment underneath. So the origin of framboidal pyrite is not disputed. There's a gargantuan literature on it. I have a student working on that in the unmineralized part of the system already. So I would have to say, great idea. I love thinking outside the box, man. But the framboids kind of bury that idea.
Well, if I'm right, there should be another deposit somewhere else that could potentially just be mechanically enriched. It should be there probably somewhere. It might be hard to find, but there are other deposits nearby that could have just been scraped up by the glacier and then dumped here.
Okay, here's another idea, and I'm letting the cat out of the bag for one of my other students. The prospectivity of this type of mineralization in the district depends on how much framboidal pyrite there is at this redox boundary where the upcoming fluids then interact with the pyrite. And so really what controls ore grade is the redox structure of the basin originally, like how much framboidal pyrite was there and why. Okay, so like you don't necessarily need to think about concentrating, like sedimentologically concentrating the reductant pyrite in order to get a high grade deposit. It may well be just a factor of what was going on, regionally at the base of or at the margins of the water column.
But by my model, it wouldn't be concentrated by reductant. It would be concentrated mechanically because it's heavier.
No, I'm not talking about concentrating it by reductant. The copper is delivered to the system in the mineralizing event, the comparatively early mineralizing event, where it alters the pyrites into pseudomorphs of pyrite, if you will, that are actually made of chalcocite or bornite or chalcopyrite. So yeah, and your other question, which was, do you need the later mineralizing event? And well, no, actually, I don't think the later event actually introduced new copper. I think it just moved it around, right? And so there's lots of places in the system where there are no caps and beards. There's not a whole lot of foliation, but there's still very high grade.
Very good. Thanks.
Thanks for your question. Good to see you.
Okay, we have several in the chat now. So Martin Perkis says, "Hi Elizabeth, thank you for your talk. This is at the periphery of the subject matter, but I was wondering what you thought the basement on which the Moashia and Nuba represents. Might it represent a horst block in a larger rift or the basin margin?" Sorry for really bungling up those words.
The answer is yes, absolutely, that's what it is. So there was a detailed sedimentological stratigraphic study of the Moale Formation done a couple of years ago. And, it very strongly implicates quite local sediment derivation and deposition based on classed identity in the diamictite. And did very detailed sedimentology on the processes by which the diamictites were deposited. So you can refer to that if you're interested in the dynamics of the sedimentary system in this subbasin. And what else was your question? Horst block. Yeah, so there seems to be an upstepping area near the northwestern margin of the Katanga Basin, where there's sort of a sub-basin that does actually drop off once you get away from that particular area, drops off into the main Katangan Basin as you go southeast.
Okay, our next one is from Ross Campbell. "Thank you, Elizabeth. Fascinating work. What do you think controls the distribution in space of the aligned versus non-aligned fabric? Is there any sedimentological control?"
I think the answer to that is no. So the aligned fabric is best developed, extremely, like comparatively well developed in the ore zone, and not really all that well developed in the least altered material. So something to do with the ore zone enhanced or allowed this pressure solution to be more effective. And I think it's probably the presence of the muscovite, which was produced during the early ore forming event. So it's intimately linked with the paragenesis of the sulfides. So once you have all of that muscovite and you're squishing the sulfides in between it and the quartz and all the other things, then that's kind of enhances the propensity for this material to be pressure solved and to transfer material at this tiny microscopic scale.
All right. Last one currently in the chat is from John and Carnation. More general question, are there any large porphyry copper deposits in the same Pan-African belt as these sediment-hosted copper deposits?
Not to my knowledge. So, and I know what you're getting at, John, is where is all of this metal coming from, right? And it's an open question. People ask that all the time, and there is no really obvious source or potential possible source other than the red beds. Yes, there are volcanics, mafic volcanics in the system here and there, but it doesn't seem to be, there doesn't seem to be enough. And there's been all kinds of work done on, you know, not all kinds. There's been some work done modeling like the mass balance of how do you get all these metals out of red beds, and you know, depending on who you ask, it's easy or it's hard. So you know, the red bed model seems to be the best explanation for now, but you know, I think the jury is still out. There must be something. I mean, there must be something more to do with what's underneath in the basement that we don't know. And you know, thanks for the absence of exposure and you know, the very poor core coverage throughout the district. Don't know what the answer would be.
All right. Well, that's all the questions that are outstanding. So we can open to have a more open discussion now. If anybody just wants to bring something up, feel free to unmute yourself. All right.
Liz, probably you wouldn't have answer to it, but I'm wondering, like, it's a giant O system, and the way from reading it, it seems like it's very widespread mineralization, and so people talk about impact of brines and evaporites, and or you mentioned rhomboidal parites, but these are very common and nothing unusual about it. So what controlled what made this system to be so productive and so voluminous?
Yeah, it comes back to the same question that John was kind of alluding to, which is there's got to be something special, right, about the source rock, and you know, is there more to it than just a red bed source? And I'm not the person to answer that, at least not right now. You know, people have been puzzling over this for such a long time, with you know, lots of controversy, let's say. So yeah, I'm afraid I'm not the person to answer that. I'm not actually an ore deposit geologist, as you know.
Thank you.
All right. Well, thanks, Elizabeth, for another great presentation today. It seems we had some good discussion despite some of the smaller audiences we've been having during these spring break weeks. So thanks again. Thanks, everybody. And we'll see you guys shortly.
Okay, thanks, Alex. Thanks, Andre.
Yeah, please.